Okay, so we want to talk about the bipolar junction transistor, or BJT. So the BJT is basically just an NPN region. And here is the symbol for it, and we have a collector, which just has the straight line. We have the emitter, which is the one with the arrow, and then the base, which is the line that comes in perpendicular to that flat part. So we look here at the NPN and we can see that a PN region that we had before was just a diode. Well, there's also a PN region on the top that looks like this. So it really just looks like two diodes with a connection in between the two diodes. Now that's kind of looks like what we have over here if I have two diodes. Well, if it seems like if I have two diodes, how am I ever going to get current to flow through this diode down? And so what really happens is that this is the wrong way to model a BJT, because what ends up happening is the region in between that has these two P regions is really narrow. So we can't use this model to analyze everything. So let's go in and look at what's really going on. So in here, you see we basically have this N region and the N region and the P region in between. And we end up getting these two depletion regions between the N and the P and the N and the P there. And what ends up happening is, but we have a very narrow region in this base. And so what ends up happening is that when you insert current into here, it's controlling the two boundaries. And so what ends up happening is that the current going in here is controlling the current that's flowing between the two N regions. So it's like this has a little control valve. And so the way that this really looks like is we have the base that is the control valve that controls the flow of current, or the flow of electrons up, which means that the current is flowing down. And that flow of this current from the collector to the emitter is controlled by the base, by this injections of holes, which changes these two depletion regions. So here it basically shows that we basically have this depletion region right here, and then we have these injections of holes, which is going to control that and get this flow across. And so this here is kind of showing with this injection of holes, you get this change in the boundary here, and then you can actually get controls across. Okay, so now let's look at the math. Now, that's a pretty brief understanding. If you really want to understand all of the physics behind everything works, you're going to have to take like a solid state physics class like Electrical Engineering 450, where you go into a lot more detail. In an electronics class like this, what we're more interested in is how do we use the devices and what are the overlying circuit models that we're going to use. So let's look at the collector current. So this collector current is the current that's going from the collector boundary down to the emitter on the bottom. And so we see that this collector current is going to be dependent on the area, the charge, the number of carriers, all these other variables, and then times this diode equation that we had before. Now, if we're conducting current, we found out with diodes that we ignore the 1, and then I get this equation right here. So in this equation right here, this looks a lot like my diode equation, where my collector current is dependent on the base emitter junction. And here's all the variables that we can see that's going to affect that RS. And then if we want to relate this to the base current, we can kind of see that the collector current is basically has some ratio, which is called my current gain, or my beta, times my base current. So if I can control my base current, I get an amplification of that by the beta up to the collector current. So here's the summary of the currents. So my collector current is dependent on that base emitter voltage, and then my base current is basically just going to be this collector current divided by beta. Now from Kirchhoff's current law, we know that my emitter current is going to be equal to the sum of these other two, so that's why I end up getting a beta plus 1 over a beta, and then that is this, and sometimes they use this term here and they call it alpha. Okay, so now that we see here is we see that by controlling the base emitter junction, I'm controlling my collector current. So we can use this BJT as a current source, and really it's a dependent current source. So the current is dependent on my V1, which is my base emitter junction, independent of the actual voltage across the transistor, so it can act as an ideal current source. So if you look right here, we have our collector current, which is completely independent of our collector emitter voltage, or the voltage across the transition. You see this voltage right here, which is VCE. And so we see that it acts as an independent current source. Whatever the voltage is here, it's going to produce whatever current, which is controlled by the base junction. Okay, so then if we want to actually do this, I can take my transistor, which is shown right here, and I can replace my transistor with this diode for my base emitter and the dependent current source for my collector emitter. And so whenever I see my transistor right here, I can remove my transistor and replace it with this large signal model, which is my diode and my dependent current source. By doing this, then I can analyze this circuit. I can analyze this circuit using everything that you learned in 240. And this is called my large signal model. So now let's look at these characteristics. So if I put a variable voltage source on the base of my transistor and fix my collector current, you see I get this exponential diode equation. Okay, now if I fix my base emitter voltage and vary my collector emitter voltage, you can kind of see that we get a flat current that's independent of that voltage, and the current is going to be dependent on my base emitter. So if I change this value, I have a different set value right there. Okay, so let's look at a simple problem. So we're going to fix my base emitter junction. I'm going to fix my collector voltage, and I'm going to put a resistor in there. Well, the current is going to be controlled by this. So if I change my resistor here, it's not going to change my current flow. But as we can see here is that the V of X is going to be equal to 2 minus my IC times my RL. And so as if my current is fixed and my resistor increases, I'm going to start going down lower and lower. Well, eventually, if I were to keep going on this plot, my Vx is going to become negative. Well, if my Vx goes negative, then you see, so if Vx is negative, less than 0, then my current's going to be flowing up, which is the wrong direction, and it's no longer going to work the way that I expected it to work. So, but as long as we don't do that, then what we can do is we can get into what's called a small signal model. So before, with my large signal model here, I basically have a base emitter diode here, which is going to be dependent on my collector current. So if I have some AC value sitting on top of some DC value, so if I have this DC base emitter voltage and I have a small change in it, then I'm going to get a small change in that current. So you see, I can just basically replace all of this with a change in voltage. So this is called the small signal model. So we said, hey, I'm not going to worry about my DC values. I'm only going to be analyzing my AC values. So this is going to be the change in current given by this change in voltage. But the problem is that I still have this diode, and so how do I analyze the diode? What does an AC, a small differential change across that diode do? And what ends up happening is if I look right down here, the change in my base current is going to be equal to the change in my collector current divided by beta. And so what we see here is that this, let's see if I can erase that. Okay, so this is the value of my R pi that goes in right here. So what we're going to do is we're going to get our dependent current source, which is going to be based off of the GM, and then also the GM is going to be equal to the I in the collector divided by my thermal voltage. So this goes in here. So I can calculate my R pi and this. And so now when I take my transistor, wherever my transistor is, I'm going to replace it with this as long as we stay in that active regime where this voltage is positive and the current is flowing down. Now we also end up getting, if this voltage, this collector emitter voltage gets too large, so if this starts to get too large, then I start to change these PN junction depletion regions because I'm pumping in too much current from the top. And so what ends up happening is I get a slight slope. So what we see here is we have what's called the early effect. So before we said that this was flat. It's not exactly flat, it has a little bit of curve, and you can kind of see that this exponential base emitter junction just changes a little bit because you're pushing in too much current from the top. And so then what we end up getting is we take into account that small slope by saying my collector current is my ideal collector current times this 1 plus VCE over VA. So the VA is going to be a characteristic of my transistor. And then the VCE is just how much voltage I'm putting across there. Well, that means that if I have a small change in this voltage, it's going to make a small change in my current. And so then I have to model it the same way I did with my R pi. And so you can see that this value here goes in there. So then I have a new RO, a little resistance that I put across this to take into account that early effect or that slope in my current. So now my variables are the R pi, the GM, and the RO to get everything to work out. And now this is my small signal model that I can replace the transistor with. Okay, so now let's look about what happens when those voltages get too high. So you see if my V from my collector to my base is less than 0, then that is no longer reverse biased. And if that happens, then I really do model it with 2 diodes. So you see now I have this forward bias diode from my base to my collector, forward bias diode from my base to my emitter. And then that's going to come in and that's going to mess up this relationship. And so you can kind of see that we're going to get a decrease in my gain factor. And so we're no longer going to be able to analyze it using my beta if we get into that saturation condition. So let's go and look at our data sheet really quickly. So here is my 2N3904 transistor data sheet. Here's the schematic for it. Here's what it looks like. It looks like a little semicircle with a flat section. If I'm looking at the flat section, the number 1 pin is on the left, which is the emitter. So you see that if I look at the flat section, these pins go emitter, base, collector. Okay, so we have all these parameters. So we come in here and you can kind of see that, oh, I can only go up to about 40 volts from my collector to my base, or 40 volts from my collector to my emitter. Otherwise, you're just going to arc through and ruin your transistor. It has a maximum current of 200 milliamps before it breaks. Okay, but what we're interested in the most is we have these two conditions. Okay, so what we see here is the collector emitter saturation voltage, so 0.3 volts. So the collector emitter, if it gets below 0.3 volts, it's no longer inactive. We can also see that my base emitter junction, if that's on, turns on at around 0.65 to 0.95. We tend to use 0.7 volts for my base emitter, and we use about 0.3 for my collector emitter. Okay, so that's what we just kind of looked at in the data sheet. And so what we end up doing is, if we're in saturation, then we're going to take and we're going to replace this transistor with two voltage sources. So these are going to be our constant voltage diode model. So between the base and the emitter, we put as a 0.7 volt source, and for my collector to the emitter, I get a 0.3 volt source. So if I'm in saturation, so let's write these down. What do we mean by saturation? So if VBE is greater to 0, so that means forward bias. Okay, and my VCE is approximately less than 0 if it were inactive. That means that this junction right here is now also forward biased. Okay, then I'm going to use this one. So this is my saturation model. Okay. So then now let's look at my collector current as a function of my collector emitter voltage. So you can see these are pretty flat going across there until it gets small enough. And so until it gets to about 0.3 volts, and then it's no longer flat, and then these currents are going to start to drop off. Each of these different lines is going to have a different base current. So this would be base current 1, base current 2, base current 3, and then we get this. You can also see down here that it says that the speed also drops when I'm down in saturation. So the transistor works a little faster up here than down there. Okay, so the last thing that we want to look at is PNP. So before, with my BJT, I had an N region, a P region, and an N region. Now I'm going to swap everything around. So now when I swap everything around, now you see that my voltages have to end up changing. So now, before, I was pushing current in, right? So with the NPN, then my current was going in. But now that I have a PNP, now my current's going to be coming out. Okay, so when my current's coming out, that means my holes are going in rather than, that means my electrons are going in rather than my holes, since everything's backwards between electrons and current. So now everything's kind of backwards. So now what we see here is that I need a negative voltage from my base to my emitter. The one with the arrow is still going to be the emitter. So let's look at this one right here. So typically when I have a PNP, you see that I still want to have my high voltages on the top and my low voltages on the bottom, and I take my transistor and flip it over. So the base is still on this side, but now my emitter is connected to the high voltages and my collectors to the low voltages. So you see that all my currents are the opposite direction. And you see we can go through and do the same process for the large signal model of my PNP. So now I have a diode from my emitter to my base. But we're going to see that the small signal model tends to be the same for the PNP. Okay, so we are all done. So let's kind of review everything that we learned. So we have basically 4 regions of operation. Okay, the first one is cutoff. So the cutoff is that if my base emitter junction is off, so this would be kind of like the base emitter junction is, or the base emitter diode is reverse biased. And in that case, it's basically just an open circuit. There's no current flow at all. Forward active. This is the main region that we want to stay in for this class. This is the one where we can replace with a small signal model. It acts as a dependent current source. This is where we're actually going to be able to make our transistor into an amplifier. So this is where we want to be all the time. And in this case, I want my base emitter junction to be positive, and I also want my collector emitter junction to be positive. And this is called forward active. The saturation is if I'm in forward active, but my collector emitter voltage starts to get too low, then we no longer have a reverse bias condition on my collector base, and that becomes saturation. Reverse active is where I basically take my forward active and flip everything around. So my collector becomes my emitter, and my emitter becomes my collector. We don't want to use this case. If you end up designing a circuit that's in reverse active, you will lose points because it's wrong as far as this class is concerned. When you go into reverse active, the transistor kind of works, but the breakdowns are a lot lower, the betas are a lot lower, and it doesn't work as well. So in this class, even though it works in LT Spice, if you do this, you will miss points. The last piece is we did our small signal model, and this is the small signal model for my base, my emitter, and my collector. So I take my transistor and replace it with this, and then I can analyze it. My R pi is, so you see R pi is connected to the base, so it's related to the base current. So it's going to be my thermal voltage divided by IB. The GM, which is the relationship between current and a voltage, is going to be equal to my collector current divided by my VT. And then the RO, which takes into account the slope in my current with respect to my collector emitter voltage, gives me an RO, which is VA. For a BJT, for a 2N3904, the VA is like about 100 ohms. And then we are done. Now you know the basics of BJTs. Now we just